Okay, so the definition of an expected count, if the outcome of an experiment has a probability P, then if you have n trials, the expected count is n times P. So an example of that is this problem right here. It says, suppose a town has about 25,000 adults in its population. If the unemployment rate in the town is 5% and you sampled 200 adults, what is your expected count of unemployment of those 200?
200 times 0.05.
Very good. 200 times 0.05. And you should have gotten 10 people that way. Okay? If an event contains many outcomes, then the expected count of an event is the sum of expected counts of outcomes. Suppose that the wet season in a region is 125 days long and there's 85% probability. And the dry season is 240 days and there's 10% chance. What is the expected number of days of rain in the year? How would you set that up? Yeah. You're on the right track. Good. And 240 times? Yep. So if you multiply those out and add them together, you should get 130.25. Okay? All right. If you observed that it rained 144 days last year in this region, then the difference is the observed, the difference between the actual rain days and the expected. Observed minus expected. In this case, it was 144 minus 130.25. Oops. And that would be 13.75. So, the expected count does not tell us what will happen in any particular case. It tells what we expect to happen in the long run. Okay? So, this is one of the important laws right here, the law of large numbers. During World War II, John Carrick, a South African mathematician, was captured by the German army in Denmark and interned at camp. To pass the time, he did experiments on chance processes. In one such experiment, and this is spelled wrong, experiment, he tossed a coin 10,000 times and observed 5,067 heads. So, yeah. Okay, in his experiment, what is the expected number of heads? Yes, because that's 0.5 times 10,000, right? So 5,000. Find the difference between the observed and expected number of heads. Yep, 67, because it's 5,067 minus 5,000 equals 67. Okay? What was the relative frequency of the heads? Okay, so this is not the expected amount, but the actual amount. So you're going to have the actual amount over the total tosses. Okay? And that equals 0.5067. So it says, what is the difference between relative frequency and the probability of heads? You're just going to take 0.5067 minus 0.5, and the actual difference between those is very small, right? 67 seems like a lot, but in the big scheme of things, it really isn't. All right. Turn the page.
Is it gonna be harder than that?
Hmm?
Does this get harder than that, or is that kind of it?
Well, no, this is not a tough one. Notice that the differences seem like a lot. However, the relative frequency differed from the probability is only 0.0067, and the relative frequency gets closer and closer to 0.5 as the number of trials increase. This is important. So the relative frequency gets closer to the expected probability the more trials you have. Everybody got that? And that's the law of large numbers. Okay? The more times you repeat an experiment, the relative frequency will approach the actual probability. Law of averages. Now this is different. When a batter comes up late in the game without a hit, a baseball sportscaster says he is due for a hit. A gambler who's had a run of bad luck will say, my luck is due to change. Both of these statements are based on principle often referred to as the law of averages. But the law of averages is not valid. Okay? You have the same probability on the next turn as you had on the last turn. Okay? The gambler who has had a run of bad luck may be correct that his luck has been bad, but he is no more likely to have a run of good luck now than when he began. The baseball player who has not gotten a hit is no more likely to get a hit now than before his slump. Okay, so be sure you understand that the probability isn't changing because he's had so many in a row. It's still the same probability. Okay, so to understand the law of large numbers is true while the law of averages is faulty reasoning, we're going to perform this experiment. Okay, so we're going to take some time to do this. I'm going to stop the video here.